is what Valgrind does. And it is just a, I guess it's if you have an understanding of explicit memory management, it's a simple to understand tool, and you just use it and you do whatever it says. It also can detect leaks, I should say that. By default, it doesn't track leaks. You have to give a specific flag. If you give that flag, it will tell you at the end, I think it's, yes, lead check for it. And it tells you at the end which blocks are no longer reachable and where they were allocated. In this case, I'm not freeing any memory, so both of them have been leaked.
It's worth noting too that you can do like cache grinds and get speed numbers for your code if you have particular hotspots you need to optimize.
Right, so there are a number of other tools, cache grind, Valgrind. I just want to like to present Valgrind. Okay. So cache grind is one tool that this instrumentation process is being used in order to collect cache hit data, cache miss data based on a certain cache model. So if you're doing architecture research, that's something to be aware of. In practice, though, the models that are freely available are actually not that good. Particularly, they don't model some of the more advanced caches of some of the Pentium architecture. In particular, there's no free model for the trace caches on the Pentium. Valgrind. So Valgrind is another one. It's a race condition checker. I'd like to show you this. For example, so here's a simple program. Traditional, or canonical, I should say, race condition. There is a counter object, I've written this in C++ here, that is being incremented, but there is no lock to protect it. And then there is a test harness down here, where if I run it with a simple argument, it simply starts two threads, then joins them, and these threads increment this counter, and they do so concurrently. And of course, this is a race condition. So if I run this simple race, run in the Valgrind, what is it? Dash tool Valgrind. So notice I've changed the tool. Now it gives me an error that describes that bug. So specifically what it says here, possible data race during write of size 4 add and forgot to So it says possible data race of item size 4, where it counted an increment called from here to here to there. But it gives more information. It says reason, this thread, the thread that did that access, that was unprotected, holds no consistent locks. And in moreover, it says this particular location that's being accessed has never been protected by anyone. So the particular location here is this one, which is in this program this counter variable. Actually, it's the count inside that one, which is here allocated on the heap right there. How does race condition works? By follows a simple idea, which is that unless it can be proven that something is not a race condition, we assume it is a race condition. Okay? Now, how can it be proven that it's not a race condition? Well, to be not a race condition, it must be synchronized in some way. One way in which it can be synchronized is by using locks. So, what this tool does is, whenever a shared variable is being accessed by any thread, it records which locks are currently held. And if a variable is correctly protected, then the same lock, really, or the same set of locks must be held whenever that variable is being accessed. So what this tool does is simply blindly records what lock is being held when a variable is being accessed. And when it sees that given, and then it keeps track of the intersection of those sets. Okay. So that is, if there's a new access and the lock that was previously held is no longer held, it will be removed from that set. And if at some point that set becomes empty, then there was no lock that was consistently held when that variable was accessed. In fact, in that case, there was no lock held at all. This is known as the lock set algorithm. And so it's a kind of a brute force method, but as you can see, it works to detect those base conditions. The second thing that Valgrind takes into account are other methods of synchronizations, such as thread join synchronization. So here the idea is that if an event that happens before a thread is started, an event that happens by that thread, when that thread runs, that those two events are synchronized in the sense that they cannot be concurrent. The second one must happen after the first one. Okay. And similarly, if one thread is waiting for another thread to finish, then whatever the waiting thread does after it has waited for that thread to finish, and what that thread that's being waited for is doing while it's running, those things are synchronized. Right? They cannot be concurrent. They cannot be happening at the same time. They cannot interfere with each other. So Valgrind knows that, takes that into account, and you can use it. I should point out Valgrind is only available in Valgrind 3.3 or 4 and more recent. It's also available in 2.2, but it was for a while not supported. So in some Linux distributions, you may have a version of Valgrind that doesn't have Valgrind.
Does it also detect like deadlocks? So if you ABB...
Valgrind, last time I tried it, it did. I think so, yeah.
It depends on the version you try?
Yeah, it may. So why? They also replaced the threading system. Okay, so if they replace the threading system, they have control of the scheduler. That allows them, if they encounter, so what is deadlock? Deadlock is a situation where your run queue is empty, you have no running thread. So you have no running thread, but you also don't have any ready threads. Okay. So your ready queue is empty, and there is a circular dependency among the threads that are blocked. So if you have control of the scheduler, then you can kick in when you run out of ready threads, and you can examine the states of the threads that you currently have in the system, and if there's a cycle in there, you can declare deadlock. The old Valgrind did that, the one that was with 2.2, and I assume this one does too, but I don't know for certain. But so yes, that deadlock will be detected as well. But you point out only deadlock that actually happens. Okay, this tool does not detect
static analysis.
Potential deadlock. No, not static, but dynamic. Okay. So you could also detect deadlock. Say you have you're violating the locking order. You take this lock in this and the other lock in one order in one thread. Another thread does it in the opposite order. So if things go bad, then there could be a deadlock. But it doesn't.